This presentation is on structural fire analysis of a steel frame with the FDS-SAFIR interface. I'm going to be presenting with Chenzhi, who was a PhD student in the Department of Civil and Systems Engineering at Johns Hopkins University and has recently moved on to a position as a postdoctoral researcher at University of Nevada, Reno. In this presentation, we will cover three items. First, I'll discuss different types of fire models that we can use and input as thermal boundary conditions in a subsequent finite element analysis with SAFIR. And I'll discuss the different coupling strategies. Second, I'll focus on the coupling between CFD analysis, specifically with the fire dynamics simulator and SAFIR. And third, Chenzhi is going to present an example of a steel frame exposed to localized fire model with FDS. So in general, in a structural fire engineering analysis, we follow a three-steps approach where we would first define and model the fire, quantify heat flux and thermal exposure. Second, calculate temperatures in the structure. And third, calculate the structural response under those transient varying elevated temperatures. With the finite element software SAFIR, we can complete the second and third step. And the first step of the fire model is an input. So we can choose different types of fire models and then apply them as thermal boundary conditions. So in the table here at the bottom, you see different options to use different fires in SAFIR. A very common option is to use design fire specified as a gas temperature function, so TG. So that's appropriate for post-flashover fires when the temperature is approximately spatially uniform in the compartment and the surfaces are then heated by this gas temperature. So when applying a function TG, SAFIR will then compute the net heat flux through the boundaries, considering convection and radiation. But there are other options. You can specify a flux, no temperature, or, and I'm going to focus on that last row, there are options to compute the flux automatically from different types of local fire models. Note that these different conditions or types of fire models can be combined in a single structural model. You could have parts of the structure heated with different methods. So how to select the appropriate fire model? When conducting a prescriptive analysis, the appropriate model is the frontier type of condition with the function for the gas temperature, which would be a predefined function such as the ISO 834 fire for prescriptive design. But when we are working on a performance-based fire design, we want to consider physically based fire. So then the consideration is whether that is full compartment fire or we would like to consider a localized fire. So in the case of full compartment fire, there are different types of models such as parametric fire or zone models, where again, what will be evaluated is the varying gas temperature in the compartment. And then this can be input again as a frontier condition in SAFIR. It can be a user-defined gas temperature function. When dealing with a localized fire, in contrast, the boundary condition is of the type flux, and SAFIR contains functionalities to consider different types of localized fire models, such as HASEMI, the LOCAFI, which is based on Heskestad, a traveling fire model, TRAFIR, and interfacing with CFD. So now focusing on this family of fire models, the localized fire models, there are a number of simplified models that are specified in the Eurocode. So the top part of the slide shows the different localized fire models in the next generation of Eurocode and where to use which one. There are specific functions in SAFIR for most of these configurations. So there is a function for HASEMI, typically used for ceiling members, such as a beam, when the flame hits the ceiling. There is a function for locaphy, for a radiative heat flux to a column. So it's possible to consider most of these considerations. Some checks must still be done manually, for example, to consider the maximum between a zone model or a localized fire. Today, I'm focusing on the situation at the bottom of the slide. So that's when we want to have a more sophisticated representation of the localized fires, and this is done using computational fluid dynamics. Specifically with the fire dynamics simulator developed by the NIST, there are two main methods to interface the outputs of the FDS calculation with the subsequent thermal mechanical analysis in SAFIR. We've discussed some of these today. So the first method is through the use of an adiabatic surface temperature. This is a fictitious temperature of a perfect insulator, which can be output from FDS, so using sensors, which have to be located in the domain with their direction. FDS will record these fictitious AST temperatures at the location of the sensors, and then these can be in turn applied in the thermal analysis as a gas temperature function. So in SAFIR, they would be treated as a gas temperature. So SAFIR would calculate again the net heat flux, considering convection and radiation with this AST temperature. That's a very valid method. It's very versatile. The only caveat is that the user must make sure to use sufficient number of AST along the structural members as well as around the sections to capture different directions and different thermal exposure conditions. That would also require then using different section types in SAFIR since the boundary conditions vary. The second method is the use of the automatic interface. So there is a function in FDS to export directly the incoming radiant intensities and the gas temperature. So FDS would print at different locations all these radiant intensities, conserving the information about directionality. And then SAFIR treats that as a flux and integrates to receive or to compute the impinging flux on the surface of the member. If you are interested to learn more on the interface, so there is a paper that describes the assumptions behind this interface between CFD and finite element software by Professor Nicolas Tondini from Trento, Professor Jean-Marc Franzen from University of Liège, and more recently with one of my students who we compared different approaches to model localized fires in structural fire engineering calculations and showed some comparison between methods and with test data. So on the slide on the right, you see some of those plots that compare the interface method against other coupling methods between localized fire and SAFIR. So how does it work? Briefly, there is a lot of information here, but the idea is you have to do first an FDS analysis and then a SAFIR analysis. Importantly, the coordinates system for the domain must match in both because there will be an automatic coupling, interfacing of the conditions. In FDS, typically it's not needed to include the structure. I'm talking here about frame members. Of course, you would need to include boundaries of enclosure walls or ceiling as they would affect the fire development, but the beams and columns should not be included. And then there is a specific command line, RADF, that will create the transfer file. Then in SAFIR, the user creates the structural analysis input file, which is needed to know the relative position of the structural members versus the fire, and then run one thermal analysis for each type of section, and SAFIR will automatically compute the temperature distribution in the members along the beams or the columns based on the varying impinging heat flux. SAFIR will also do the spatial and temporal interpolation and integration of radiant intensities automatically. The file structure will look like this. First, on the left on FDS, when you run the calculation, there is a specific TXT file that is generated with all the interfacing information and data. So this file has to be named cfd.txt. And then on the right, the SAFIR analysis looks as usual with a structural input file and different thermal input files for the different types of elements. But notice that when SAFIR goes through the thermal calculations, it will generate many TEM file here for a beam based on just one run of input file. So these here corresponds to the 2 points of integration for one beam finite element. And in this example, there are 11 finite elements for the columns. There will be 22 TM file generated. The torsion calculation needs also to be completed, and then you can run the structural analysis. I will now hand it over to Chenzhi, who will present an example.
Thomas just briefly introduced the overall workflow of the FDS-SAFIR interface. Now I'd like to go a little bit detail about use an example of steel frame to introduce how we apply this method in analyzing the localized fire. So here, the steel frame we use here is extracted from a two-story steel concrete composite building by in a recent NIST fire test. The section size, the gravity load, and also the geometry are identical to that test. And also on the right-hand side, I shows the relatively location between the fire and the frame. So here we didn't consider a symmetric location between the frame and the fire. Instead, we move the center line of the fire a little bit away from the center line of the frame to see whether the interface method can capture this asymmetric behavior. The fire we considered here is based on a combustible test of a SOFAR conducted by the NIST. The peak heat release rate, time to peak heat release rate, and total heat release are obtained from the test. And so in the next slides, we use this information to establish our FDS model. So the first step is to choose the domain size. It needs to be noted that, as Thomas said before, the coordinates of the FDS model must be consistent with the coordinates of the structure model in SAFIR. So here, again, the domain size of the FDS must larger than the size of the structure model to make sure every point of the structure model can have corresponding thermal results from the FDS model. So here we consider the ceiling in the FDS model, and in the direction which is the face towards us, we set it as open. The fire block size 2 meter by 1 meter. The mesh size here we choose is 0.1 meter, which is developed based on, first we use recommended range by the FDS user guide, and then we conduct a quick sensitivity analysis to make sure to balance the FDS calculation time and the accuracy. And next slides, we have we showed the animation we obtained from the FDS model. We can see the fire is restricted below the ceiling, and we can see how the fire propagate and impact its surrounding environment. In the next slides, now we have built our FDS model, and we've run our FDM model and obtained the transfer file, the RADF file. Now, next step is to run the thermal analysis and mechanical analysis. So in the thermal analysis, we use 2D analysis of the beam sections. For all the surface that exposed to the fire, we assign a thermal boundary condition of flux named CFD. For example, here we have a column. All the four sides of the column is exposed to the fire. So here the frontier CFD, we assign it to all the column surfaces. In the mechanical analysis, we build the the coordinates is consistent with the FDS coordinates, and for the column N, we assume it is fixed to the ground, and we use a simple connection between the column and the beam, which means there are some relaxation to release the moment in the connection. And the yeah, so here we extracted the temperature information from the SAFIR results. The first observation we observed is that so along the length of the beam, we can see for beam section that is closer to the fire source relatively has higher temperature compared with section that is relatively far from the fire. And also, we can clearly see that the interface method captured the asymmetric behavior in the beam sections, which cannot be done by traditional localized uh, model HASME. So in the HASME localized fire model, the all three sides of the beam section is exposed to the same heat flux, which means we cannot capture the asymmetric behavior. So beside the beam section thermal response, we also extract the thermal response in the column. Again, we can see the asymmetric behavior in the column section for the surface that is close to the fire relatively tends to have higher temperature, and the left column has a higher average temperature compared with the right column, which is far from the fire. In next slides, we also extracted the mechanical response of the frame from SAFIR. On the left side, I plot the horizontal displacement at the mid-span of the beam. We can also see the beam tends to um, toward uh, deform towards the fire source out of the plane. And on the right-hand side, we can see that the column close to the fire has more deformation compared with the column away from fire. This observation is reasonable, and during the whole localized fire process, there's no failure happen for the steel frame. And in the next slides, we conduct some sensitivity analysis to see to more or less validate uh, the reliability of the interface method. So here we use two different column section size. One has a higher thermal inertia, the other has a relatively smaller thermal inertia, and we can see the maximum temperature in the column section is different, and the lighter column section has a relatively higher maximum temperature. And in next slides, we also compared the interface method with the AST method. So as Thomas said before, to use the AST method, we have to place as much sensors as possible in the FDS model to capture the temperature variation around the section as well as uh, along the beam element. So for example, here for the steel beam, here we assign 5 sensors in each section. So because AST sensors are directional for at the same location. For example, the bottom flange here, we have to put 2 sensors at two different direction to make sure we can capture the temperature at the up flange of up surface of the bottom flange and the downward surface of the bottom flange. And in next slides, we compared the thermal response between these two methods. First, let's if we compare the temperature distribution in the section, we can see there's almost no difference between these two methods. And we also when we go to the temperature time curve, we can see there is a slight difference between the ST method and the interface method. It is because in the interface method, for each beam element, there's 2 points of integration, and the interface method will automatically extract the thermal response at the location of each point of integration, which means for the same beam element, at the 2 point of integration, there will be two different thermal response because the radiation fell at these two locations are different. But in the AST method, for the same beam element, at the 2 point of integration, they have the same boundary condition as then we can see there's the same response at the 2 point of integration. But overall, the AST method agree well with the interface method agree well with the AST method, and the extracted temperature in the AST is between the 2 point of integration of the interface method. In summary, I want to quickly discuss about the advantage of interface method. So once we obtained the radiation file, the CFD TXT from the FDN model, we can change the position of the frame, and we can change the section size with and then rerun the thermal analysis and the structure analysis. We don't need to rerun the FDS model. But in the AST method, once we change the structure design, we have to reposition the AST standards and rerun the FDS model, which might be a little bit takes a longer time. Thank you. I'll give the stage to Thomas.
Thank you, Chenzhi. So briefly, in this conclusion, just 3 points. We discussed the fact that there are many models available to model thermal exposure from fire so that they can be then coupled with a finite element analysis. And specifically, we discussed when to use FDS or CFD type model. When we do so, there are two main procedures to use the CFD data in SAFIR. The adiabatic surface temperature method, which is treated like a gas temperature at the boundary, or the automatic interface methods. Both have their interest. We've compared them and they give comparable outcomes. With the AST, there needs to be a large number of sensors and different section types, but that can be automatized also with a script. And with the interface, SAFIR will automatically capture the directionality and integrate, including shadow effect of the section of the members, which is an advantage. Finally, we showed an example 3D frame analysis to illustrate how that works and the fact that using the interface with an asymmetric or offset fire, we did capture asymmetry in the thermal response as expected. So thank you for your attention, and we're happy to take any questions.